of the computer science in CMU. He led the NERCA lab, the learning and control for agile robotics. He also had countless faculty positions in the electric and computer engineering and mechanical engineering department. He completed his PhD in 2022 from Caltech, advised by Sun Zhengchun and Yi Songyue. He received a B Bachelor from Tsinghua University in 2017. From 2022 to 2023, he was a postdoctoral scholar in the Paul Allen School of Computer Science and Engineering at the University of Washington. And Professor Guangya is an expert in the humanoid locomotion and local manipulation part, and he will give us an excellent talk about his recent research. Thank you all.
Thank you. Thank you for the introductions. Hey everyone, it's very exciting to be here to talk about some of our recent research. And I really like this tutorial. And actually today I'm gonna give you some sort of like Sim2Real 1.0 for humanoid. It's actually my first time in person CVPR. It's really exciting to see how we synergize some computer vision techniques and deep learning techniques with robotics. I think that's going to be one of the most exciting topic in the next 5 years. So let's get started. So the topic today is going to be from Sim2Real 1.0 to 4.0 for humanoid whole body control and the local manipulations. This is 3 main papers I'm going to discuss today, and of course the techniques behind them. And the first one is called Omni-Tool. It's basically a real-time framework that can translate human motions to humanoid motions. And the second paper is called ASAP, which is an agile whole body control, Sim2Real real-to-Sim framework for controlling this humanoid to achieve some really agile whole body maneuvers. The third work is called FACON, which is a local manipulation framework for forceful object interaction task. As you can see, you can see these videos. The humanoid can open a door, pull a card, etc. Okay, let's get started. I want to start with something different from Sim2Real RL, which is learning from teleoption data or learning from videos by behavioral cloning. As we know, like this is like really promising, like in the recent, I would say 3 years. And the basic recipe is pretty simple, right? We do behavioral cloning BC from labeled actions. Label action here refer to either human teleoption data or like some human videos. And the action space in this case is typically very simple. It's either jaw angle of the arm or in the effector pose of the effector. And the low-level control is relatively simple and accurate, right? Typically, people just do PD control or inverse kinematics plus PD. Just want to give you 2 examples. And the first example is a recent release, Pi 0.5 from the startup company Physical Intelligence, which is a pretty big VLA model, vision language action models, learning purely from teleoption data. I mean, this video is really impressive in my opinion, because it's an open vocabulary, very long horizon manipulation. I believe all the objects in this video are unseen in training environment, in training time. So it's pretty impressive. And the second example is, I think 2 weeks ago, the new demo from Tesla Optimus. You can see in this video, the Optimus humanoid can do a lot of like interesting household tasks. Like put a trash bag in the trash bin, clean the table, etc. And this is a little bit different. Learn not only from teleoption data, it's also learn from some sort of human videos. Okay, right? This is like very promising. Seems like we have some scaling law, sort of, for embodied intelligence, right? The more teleoption data you collect, the better performance you have. Not only industry, right? In my lab, also work on some similar topics. This is a collaboration with Xiaolong's group in UCSD. This project is called Humanoid Policy, Human Policy. And in this video, all the diagonal terms are humanoid data, and non-diagonal terms are human data. So what do we do in this project? We figure out a unified representation that we can jointly train a policy from both human data and humanoid data. So yeah. So I know you're waiting for however, because if I keep talking about this, it's become a reality talk, right? It's nothing to do with the Sim2Real RL, right? So here's the however. So if you realize all these tasks previously mentioned are basically quasi-static and pick and place, or like almost pick and place, right? Like how about for those tasks, right? Those tasks involving agility, especially whole body agility. For example, like this athletic maneuver, like basketball, or like ask a human or humanoid to pull or push a heavy cart, open a door, or like holding and moving a box. We will quickly realize for those tasks, it is very hard or like impossible to teleoperate. Because if you can teleoperate, you already solved the problem, right? Imagine if you can teleoperate a humanoid to play basketball in this way, you already solved this, right? If you can teleoperate a humanoid to pull a very heavy cart, you already solved this problem. And also, it's very hard to get label action for free. It's very different from pick and place, right? Imagine if I ask Michael Jordan, I want to learn fadeaway jumper. Could you tell me your jump trajectory? And he probably will think I'm insane because that's not the way human learn motions, right? It's not the way human learn skills. Also, it's very hard to use a simple low-level controller for tracking, right? All previous like Pi and the Tesla demos, right? They use a PD controller as a low-level controller for tracking because the dynamics is very simple. But for those examples, it's very hard. So in other words, all this human video, human motion skill doesn't directly tell you robot joint control, as you can see in the right figure, right? And we don't have this data. We don't have this, for language, we don't have next token prediction for those tasks. We don't have this label robot joint control data for free. That's, in my opinion, the biggest challenge in onboarding intelligence is how do we get the physics aware information, right? And learn this. Yeah. So another perspective is system 1, system 2, right? For those not familiar with system 1, system 2, and system 1 refer to some intuitive and instinct thinking, right? It's like our cerebellum, right? Our like low-level control, balancing, all this kind of thing, right? It's a little brain involved. And system 2 refer to, rational thinking, right? Like a slow and very, deliberated, and basically we are, as a human, we are very proud of system 2. I don't think we are proud of system 1. We basically take it for granted, right? Our agility, our dexterity. So I think, however, right, most dexterity and agility, especially coming to whole body, come from system 1. And I suspect most human teleoperation involve little or zero system 1. Because when you teleoperate a robot, by definition, you're using a rational thinking to control the robot. It's very hard to map your dexterity directly to robot dexterity, right? So here comes the question, right? How do we actually learn system 1 agility and dexterity? So my answer today is we need a model, or we need a simulator, and we need to do Sim2Real learning. Yeah. And as you can see later, the definition of a model and a simulator could be very broad, and we will get into this. And another thing I want to mention is this slide doesn't conflict with the success of VLA. They can coexist, because VLA exactly give you a very good reasoning for system 2, and this everything I present start from this slide is more like for system 1. They don't conflict at all. We should synergize them. Yeah, okay, let's start the journey, right? Sim2Real. Like, fortunately, it's not a new topic in control and robotics community. So the control and robotics community has been working on Sim2Real for many decades, right? I call this Sim2Real 1.0. Basically using a simplified model with some online reasoning, right? It is how it works. We start from some like reduced order model. For example, for humanoid, you can simplify the humanoid into a very simple inverted pendulum, right? For quadruped, you can simplify the quadruped into a very simple single rigid body model. So basically, all these models are a simplified abstraction of the high-dimensional dynamical system. So once we have these analytic equations from the simplified model, then we do something called MPC, like online model predict control. If you're not familiar with, you're basically solving a bunch of optimization problem. You have like dynamics constraint, you have inequality constraint, you're optimizing cost function, right? You're solving this in real time. You're figuring out what action give you best result, right? Predict independent model, right? And this is happening online real time. And the output of this procedure is action AT, right? and we directly execute this action AT on the robot, right? That gives you a lot of impressive results. This is just one example. This is MIT cheetah jumping onto the table. This is exactly doing what I said. Simplified model, online reasoning. So if we think about this, this is really fascinating, at least to me, because there's no pre-training. I mean, it's very different from language model and vision. There's no learning at all, right? What you do is 100% online, very fast, real-time inference, right? You're solving an optimization problem iteratively, very fast. So, and simultaneously, you will realize, okay, this is pretty foolish, right? In the sense that it doesn't have memory, it doesn't have pre-training. Every time it encounter either new or old scenario, it need to resolve a big optimization problem, right, to make it work. Yeah. So if you want to know more details of how to solve this, in general, for convex problem, it's pretty straightforward. And for non-convex problem, it could be tricky. It's why the control and robotics community spent like a few decades developing efficient, optimal control solver. For example, you can do sequential convex programming, you can do iterative LQR, you can do DDP, whatsoever. But in general, solving this could be tricky. Okay. And we can do slightly better right now. I call this Sim2Real 1.5, meaning that rather than using a simplified analytic model, we can use something called simulator, right? This is our recent work called DLMPC, which is the best paper award finalist at this year's ICRA. So the procedure is very similar. The only difference is we upgrade the previous analytic simplified model to a full order simulator, right? You can use NVIDIA SXGym, SXLab, or Genesis, or Mojuko, whichever you prefer. And we use advanced sampling-based method to figure out the similar problem, right? We optimize the trajectory real time, right? And again, the output of this program is action, and we directly execute this action on the robot. And here are some examples. This is a quadruped jumping. You can see like real time, and this is like the ball spinning, fingertip ball spinning in simulations. I just want to play again. I think it's pretty interesting. You can see how the DEX hand rotate, spin the ball using fingertip. And this is a human or local manipulation. So all the video are real time. Again, there's no learning. There's no pre-training. So because the program figure out how to optimize the control sequence real time online. So it's pretty impressive and it's pretty interesting. However, if we compare to what we need and we compare to especially reinforcement learning, we will realize two limitations. One is this is still pretty slow, right? You need to solve a very big optimization problem real time. And also, this procedure needs state estimation because you need to know where the robot is. You need to know X0 here, right? To start to being able to figure out what action give you the best consequence because you need to know where the robot is, right? Yeah. So how to tackle these two limitations? We have Sim2Real 2.0, right? Sim2Real reinforcement learning. I call it Sim2Real 2.0. And here is how it works. We start from some physics-based simulation. Again, ASAC, Genesis, Mojuko, whichever you want. And we create a massively parallel training environment for our humanoid agent, for example. Like we put a virtual humanoid, right, in the virtual environment, and with GPU to massively parallel. For example, typically we do 4,000 or 8,000 such environment. And to make training robust, to make the policy robust, oftentimes we randomize the terrain and we add perturbations, we add random force, just make the policy robust. And then what we do is something called policy optimizations using algorithms like PPO. So what we do is we optimize the policy pi theta. The input to the policy is observation OT, and the output of the policy is action AT, right? And finally, we deploy this trained policy pi on the real humanoid robot, right? This is a pretty straightforward pipeline. And the key difference from MPC is what we to real is policy pi, not A, right? Meaning that we don't solve any training or reasoning online, right? What we to real is a policy pi. So I think there are two reasons why this pipeline is extremely successful, especially for locomotion in last 5 years. So number one, massively parallel policy gradient method, especially PPO, is such a strong policy optimizer. It can solve so complex, optimal control problem offline. And the second, I think we take for granted is reinforcement learning doesn't really care about its POM-DP or MDP, especially, empirically speaking. And this procedure doesn't really need explicit state estimation in the real world. Because the only thing like reinforcement learning policy need inference time is observation O, right? O could be vision, O could be proprioception, O could be MU. It doesn't have to be robot state, right? And this actually give us a huge design choice space. For example, is why you can do teacher-student, you can do distillation, you can do asymmetric active critic. That is because, right, the design of O is really flexible. It doesn't have to be the robot state. All right, this is a Sim2Real 2.0, and I'm going to give you 2 examples for humanoid under the umbrella of Sim2Real 2.0. Okay, the first example is H2O, human-to-humanoid whole body control. So the goal of this work is we want to build an interface between whole body human and humanoid motion. So we want to translate from human motion to humanoid motions, right? And once we have this interface, right, we want to do a lot of things. First, we can do whole body teleoperation because we can real-time translate, right, human to humanoid. And we can do imitation learning, and we can do, we can integrate this interface with foundation models like VLMs. So the key idea of H2O is exactly Sim2Real 2.0 I just described from large-scale retargeted human motion dataset. So before going to detail, let me just play this teaser video for you to give you a sense of what this framework can do. So this part of the video, my student was wearing Apple Vision Pro to remotely control his humanoid. And I want to emphasize this is not just upper body teleoperation, which has been done. It's whole body teleoperation, right? It's upper body, lower body, and the torso, yeah, everything. And this video was released almost 1.5 years ago, and I think Unitree G1 can do a lot better. This is still H1. Yeah, the humanoid walk to the bench and grasp the knife. Nowhere is not going to hurt you. Just gonna cut a cucumber in a second. Yeah, and this video is no cut, it's one-shot video because we want to emphasize humanoid robot is general purpose, right? It can do many different things. And after cut a cucumber, it starts sweeping the floor, step back and sweeping the floor. Yeah. And finally, say hi to you. Yeah, this is a this is a one-shot video. And I can do many different things like working the plant, a lot of manipulation tasks, and play many different sports, badminton, table tennis. And this is how teleoperation works, boxing and drawing. And this part is not teleoperation. We integrate the model with GPT-4o, and GPT-4o can control the humanoid autonomously. And this part is also not teleoperation. We learn diffusion policy from the teleoperation data, like humanoid autonomously do some local manipulation task. This is a verbal instruction. We speak to the humanoid can react. To have a humanoid paper, you have to bully the humanoid to prove your method is robust. So we did that. And we also did some outdoor locomotion, right? It's a single neural network, single policy for all the scenarios in these videos. I know I play this video very fast for the sake of time. If you want to check out more details, go to the website. And everything is open sourced, including training, deployment, Sim2Real, and we also released the data set. Yeah, if you're interested, feel free to check it out. Okay, how it works. So as I said, it's Sim2Real 2.0 from a large-scale humanoid motion dataset. So there are 2 steps. Step 1 is we need to create a large-scale humanoid feasible motion dataset. Because at that time, like 2 years ago, this thing didn't exist, right? A humanoid motion dataset. So fortunately, right, from vision community and from graphics community, we have a very high-quality human motion dataset. Like, for example, AMAS, right? Corresponding to the first row here, right? The first row is, some motions from the AMAS. You can see it's a very high quality mocap data. So, but we cannot directly use it. Why? Because even though humanoid looks like human, it's still very different in terms of like physical capability, in terms of like physics parameters. So we need to do something called retargeting. So we need to translate these human motions to humanoid motions. So to do retargeting, we first did something called like kinematic retargeting. So what we did is we did shape fitting using inverse kinematics. So basically, we found the simple model, the human model that is closest to humanoid. Then we do inverse kinematics. We get a second row. It's why the human model in the second row is very weird, because it is the closest human model to humanoid. However, this procedure is purely kinematic, it's purely geometric. It is not aware of physics. So we need to do something called physics-based retargeting to get the third row. So more precisely, what we did is we trained a privilege tracking policy in simulation using RO to track all the motions in the second row. And why I call this privilege tracking policy the pink policy? Because this policy knows all robot state. This policy is not reliable. It's not practical at all. It knows everything in simulation. So the goal of this policy is to track the second row. And this policy can generate a humanoid visible motions and filter out impossible motions. For example, in the third row, the last motion, right? The last motion is too hard for unitary H1. So we just remove it, right? And the first four motions are rule out trajectory from the RO policy, and that will be the data set. Yeah. So basically, this procedure, the idea is we do something called retargeting to translate what human can do to what a humanoid can do to make sure all these motions are learnable, right, by the humanoid. However, this step one is not enough. As I said, this privilege tracking policy is not reliable because in the simulation, it's privileged, it's not robust. So we need to do the second step, Sim2Real RO training. And this is a fairly standard pipeline. We did something called distillations, also called teacher-student framework. So this privilege tracking policy, the pink policy, is the so-called teacher policy. It's privilege, it knows everything, right? And we distill this privilege tracking policy to a deployable student policy, the blue policy, right? And compared to the privilege policy, the deployable student policy is very practical. It only knows observation in the real world that is available, right? And as you can imagine, we add a lot of domain randomizations for robustness, right, to make sure the student policy is robust. And this idea has been very standard in locomotion in last 5 years. And what is interesting is like, I think the original teacher-student idea came from vision community. So actually robotics people adopted this. So this is why I think this workshop is very exciting, is why I encourage people working on vision. So think about what technique in vision can translate to robotics. Yeah. Okay, and I want to mention that the H2O pipeline is very extendable. I think the main contribution of H2O is not the result, it's the framework. So we actually define 2 critical steps to learning humanoid motions from human motions. So step number 1 is we need to do some sort of motion retargeting and learning a tracking policy in simulator, right? To track all these human motions and do this motion retargeting. And step 2 is we need to learn a student policy, right? That can be deployed in the real world. And either step 1 or step 2 is very flexible and can be extended. For example, the motion source in step 1 is very flexible. What I showed is learning from mocap, like AMS, but you can also learn from video. You can also learn from other resources. And step 2 is also very flexible, right? The student policy can track many different key points. It can also be vision-based, right? It really depends on how you distill the teacher policy to student policy. Just want to give you 2 examples of follow-up work. This is like a framework called Hoover from NVIDIA. They actually changed step 2. In this video is a little bit scary, but it's also very cool. Each humanoid in this video corresponds to different student policy. They actually learn many different students from one strong teacher. Yeah. Like some students is tracking John angle, some students is tracking like a kinematic pose, some students is tracking just center of mass. Yeah. And another example is a recent paper, Video Mimic from Berkeley. I really like this paper. They changed step 1 from mocap to video. They actually learn from egocentric video in the wild. This is really cool, right? You start from like egocentric video in the wild for human video, and you translate it to humanoid motion in the real world on unitary G1 robot, right? This is like the sci-fi concept, right? The video in, humanoid motion out. Yeah. All right. This is the first example for Sim2Real 2.0, right? How we learn from human motions. And I want to give you another example very quick, is how to learn without human motion. This is like the opposite, right? This framework is called vococo, learning whole body control with sequential contact. So this is like opposite. So we want to explore whether it's possible to learn without any motion priors. So we want to learn a long horizon skills from scratch, right, without any priors. So I don't have too much time going into detail, but the highlight, the key idea is it is very hard. So we need to design some we need some actual design to make it possible. So I want to show some result. We can learn like this parkouring stuff in simulation, again, without any motion priors, just learning RO from scratch. Translate this parkouring to real world, like continuous jumping on stairs, and some interesting climbing dance. It's pretty funny. There should be a background music. Yeah, again, it's all learning from scratch without any motion priors. Last demo I want to show is this bidirectional cliff traversal. We asked the humanoid to go through a cliff. You actually need the upper body to support. Yeah, and some anywhere to anywhere local manipulation. The humanoid can grasp a box and move from location A to location B. Yeah, again, this is a learning from scratch. And we figured it's very hard for reinforced learning to explore if we just learning from scratch. So the key idea of this project is we decompose a long horizon skill into a sequence of contact goals and task goals. And learning from scratch without motion prior is hard. We need to decompose the task into some sub skills to make it easier to learn. Yeah. So basically, I present two works for Sim2Real 2.0, one learning from motions, one learning from nothing, right? One learning from scratch. So let's summarize what's wrong with it, because the demo seems pretty cool, right? The humanoid can do many different things using Sim2Real 2.0, but what's wrong with it, right? What's wrong in its Sim2Real process? I do think the Sim2Real process has some fundamental issues, like the Sim2Real gap is large, unintuitive, and very hard to quantify. You don't know what's going wrong. And Sim2Real tuning need very tedious reward tuning, curriculum tuning, and domain randomization tuning. The best method, unfortunately, is still graduate student descent, GSD. And it's very hard to encode prior physics, right? Very poor sample complexity is unsafe. And last point is really interesting. If we compare with Sim2Real 1.0 or MPC, we realize this framework is opposite. There's no online reasoning. There's no like real world learning. Like once you learn policy from your simulation, you're done because the policy is frozen, right? The only learning happens is in simulation. Yeah, there's no online reasoning. There's no real world fine tuning. There's no like adjustment or like anything. So how do we do better? Right? I will propose Sim2Real 3.0, but let's check it out, right? In another perspective. Yeah. So this is my understanding of what happens in Sim2Real for Sim2Real 2.0. So the x-axis is the policy parameter. Let's assume it's a scalar for simplicity. And the y-axis is the performance, right? Performance of the policy. And the green is what happens in real world. And orange is what happens in simulations, right? And there are two challenges, right? Challenge number one, there's a huge gap, right? There's huge Sim2Real gap, between the green line and orange line, right? And the same performance doesn't really transfer to real, right? And the challenge two is this orange curve is nasty, right? It's the optimization landscape is super complex, and reinforcement learning could easily hack it, right? For example, if reinforcement learning give you the blue point, right? It give you very good performance, almost perfect in simulation, but it give you horrible performance in real world, right? Because reinforcement learning just exploits simulation dynamics, right? Which is different from real world. Is why I call this a bad policy, right? What do we want actually is a star, right? This is a good policy, right? Give you good performance in both sim and real, right? Typically in practice, how people conquer this challenge is still human in the loop, right? Gradual student descent. You just deploy the policy in real world, you observe some weird thing, you back to the simulation, you change some reward, you add new reward, and you go to the real world again and and solve this. But what I propose is something different. That defines Sim2Real 3.0. What I propose is we should do real to sim. But we should do some sort of real to sim to reduce the sim to real gap, to make the green line closer to the orange line. And we should also do structured reinforcement learning. We should give reinforcement learning some priors and inductive bias to make the problem have a smoother landscape, right? To make the orange curve a little bit more smooth. Yeah, let's go to detail. Let's start from like sim to 3.0 real to sim. But the idea of real to sim is quite natural, I think. We want to create a feedback loop, right? From real world back to simulation, right? Meaning that we want to learn some sort of like a residue, right? From real world back to simulation, right? To bridge the gap between real world and simulations. So very naturally, I guess if you think about, can we learn a word model? Can we learn a residual word model, right? Can we learn a residual dynamics, right? This is probably the very natural idea. So fortunately, for other robotic system, people already done that. For a simple robotic system, especially for quadrotor, for flying robot, like aerial robot. This is like some of my PhD work, like on neural control family. So what we did is we start from this, the black part of the equation, the simulation, right? The Euler-Lagrangian equations, very standard. But this equation is not accurate. The F is the residual dynamics, which is annoying part. For example, aerodynamics. So what we did is we learned a neural network F hat to approximate this F, right? You can think of this F hat as a residual word model, right? And once we learn this F hat, which is a neural network, and we design a controller, pi, right, which is conditioned on F hat. And sometimes we need to regularize F hat for control theoretic guarantees. This works pretty well for quadrotor, right? For example, this neural lander, the drone can land very smoothly, and the neural flight, we use meta learning to learn dynamics, and the drone can adapt to a time variant wind condition. And this is extension to area manipulation problem. The drone can draw some letters and calligraphers on the wall. So it works very well for simple robotic system. So how about humanoid, right? How about learning a residual word model, residual dynamics for humanoid? Meaning that, again, we learn a residual function f hat, we put to simulator. The new simulator is going to be f sim plus f hat, right? And you train a policy using f sim plus f hat, right? This is basically some sort of model-based RO, right? And if you're familiar with Dyna, this is basically what Dyna does, right? You learn a kind of like a model, and you perform a model-free RO by treating the learned model as a simulator. Yeah. Does it work? Unfortunately not. We tried very hard, but we realized humanoid is too complex. At this stage, it may be a bad idea to learn residual dynamics, right? Because we really need F hat generalized very well, which require a lot of real-world data, the F hat, and also, right, we need to regularize F hat heavily to ensure F simulation plus F hat still makes sense, which is very challenging. For example, how do you know, right, that the energy is still conserved? How do you know the momentum is still conserved? This kind of thing. And finally, don't forget, we have a very naughty boy PPO. It's too strong, right? Whatever you learn in F hat, that will be exploited by reinforcement by RO. So all these reasons together, we try very hard, but the performance is not good. So here I'm going to propose an alternative solution. Rather than learning a residual dynamics model, can we learn a delta action model, right? And the framework we propose is called ASAP, right? Learning a delta action model to match sim and real, aligning simulation and real world physics. So here's how it works. So we pre-train a policy pi in simulator, and we rule out this policy in the real world, and we get a state and action trajectory, X, R, A, R, and the superscript R mean real world, right? It's a trajectory in the real world. And then we're gonna replay this action trajectory AR in simulation. We just replay it in simulation, like open loop, right? And we get a state trajectory XS. The superscript S means simulation. And because we have Sim2Real gap, XS will be different from XR. Otherwise, you have perfect simulation. And then we're gonna train a delta action model, delta A, right? Which is a neural network. And we train this in simulation. The objective is once we augment AR with delta A, the resulting trajectory in simulation, XS, will be very close to the trajectory in the real world. Right? In other words, this delta A with delta A, right? The replay trajectory in simulation is close to real world. Right? And without delta A, it is different. And with delta A, the replay trajectory in simulation is close to real world. So, right, if delta A did give you these properties, you can imagine pi plus delta A in simulation is similar to pi in real world. Therefore, we freeze delta A in simulation, and we roll out the pi plus delta A. We fine-tune pi, and finally we deploy pi in the real world. Yeah, so basically delta A is some sort of like reduced action model that align real world dynamics and simulation dynamics. So I just want to give you some example of how it works. This is like a unitary driven humanoid single leg balancing problem. And the left video is before fine tuning, the right video is after. I want you to pay attention to the ankle. You can see before, it barely works because the left ankle is shaky a lot, right? It's shaking a lot, right? The left foot, the ankle part especially. And the right video is after fine tuning. You can see it's much more stable. Because in this case, delta A kind of learn how to compensate, right? This ankle, right, uncertainty, this mismatch between sim and real. Okay, and this framework works very well for agile whole body maneuver like this. If you play basketball, soccer, this is some iconic movement. This is Kobe Bryant fadeaway jumper. We actually slow down the video, not speed up, just to make it look better. We slow it down, like, yeah. Just want to play again, right? Just like single leg jumping and landing, right? It really need a good dynamics, right? And this is like a celebration movement from Cristiano Ronaldo. You can see the robot jump and make a 180 turn, right? Similarly, we slow it down like by quite a bit. Yeah, they all learn from like human motions, similar pipeline to H2O, but we in these two videos, like one neural network control one motions. We don't generalize, between different tasks. Okay, just want to give you more intuitive and more detailed analysis of ASAP. So first, how to train delta A, and this is basically another reinforcement learning problem in simulation. The objective is to get XS, the simulation replay, close to real world trajectory. This is another reinforcement learning tracking problem. So why it makes sense? Because intuitively, pi plus delta A in simulation is similar to pi in real world. So delta A effectively aligns sim and real dynamics. And why is it different from a classic control idea called iterative learning control? And the idea is very similar. And ASAP is a deeper version of it and learn a closed loop delta A. And typically in iterative learning control, delta A is open loop sequence. And why don't we call delta A a residual policy? Because it is the feedback neural network policy. I mean, it is a closed loop feedback policy, but I want to highlight delta A is shared by all tasks, right? Pi 1, pi n corresponding to different motion, they share delta A. Because we don't want delta A to do any task specific stuff. We want delta A pay attention to the dynamics. Yeah, this is why we don't call this residual policy. We call this a residual action model. And finally, I want to give you intuitive examples. For example, in real world, somehow the robot motor is 80% as strong as sim for whatever reason, which is common, by the way, right? The robot motor is 80% as strong as simulation, meaning that the policy output will be only executed 80%, right? AR just 80% of pi, right? But in simulation, it's perfect, right? You see the gap? In simulation, the AS is perfect just from pi. In real world, somehow it's discounted by 80%. So in this case, our algorithm will give you delta A is negative 0.2A, right? Delta A will tell you, hey, in real world, actually you should expect 20% motor degradation, right? And we can learn this. And you can imagine if when deploy data in simulation, the fine-tune pi will compensate this 20% motor degradations. Yeah, this is like kind of a very intuitive example of why it works. Yeah. All right, I think I will skip this slide. Another solution for real to sim, delta A could be a little bit complex and it need RO. Another solution for real to sim is system ID, right? System ID is the oldest real to sim, right? Because what we learned is not a neural network model or a policy. We just identify parameters, right? We deploy the policy in real world and we identify simulation parameter theta star. We go to the simulation, right? Theta star, theta is the parameter of the simulator. However, the main challenge for humanoid is this f theta, its f sim theta is neither differentiable nor smooth. So system ID of humanoid could be very hard because this f sim theta, this function, is very, very complex. So recently we released an open source framework called SPI Active, doing sampling-based system ID with active exploration for Leggy robot. So I don't have time going into detail, but the basic idea is we use the policy that maximizes the efficient information to collect data. And just want to show you some demos. And in these videos, the task is velocity tracking, is open loop velocity tracking. And we don't have any position feedback. The robot is bland. And the left is ours. You can see the quadruped can pass these pillars, and the red is baseline. And this is jumping, right? After system ID, the robot is very accurate. This is humanoid velocity tracking. The humanoid is supposed to stay on this green line. Yeah, the left is after system ID, the red is before. Again, I want to emphasize the policy in this video is bland. Policy doesn't have position feedback. So this video highlights why system ID is important. And the default simulation could be very off. Yeah, if we don't do careful system ID. Yeah. All right. I want to spend 3 more minutes, 4 minutes for structure RO, and then we can conclude and for questions. So another idea of Sim2Real 3.0 is structured RO, right? If you remember in this figure, in this Sim2Real figure, another big problem is this orange curve is too complex. It's very hard to tune, right? The orange curve landscape is so nasty, right? And the idea is, can we leverage humanoid structure or like any robot structure to design a better policy architecture, right? Such that we have a better, RO optimization landscape. We have a smoother curve, right? I call this structured reinforcement learning. Okay, the example I'm gonna give you today is called a FICON, which is a dual agent reinforcement learning framework for force adaptive local manipulation. So the task here is heavy duty local manipulations. For example, in this video, we ask the booster T1 humanoid to pull a very heavy cart. The humanoid here is just 30 kilo, but it needs to pull an 85 kilo cart. The left video is a baseline. You can see the cart barely moves, right? Because it need to do force adaptation, right? It need to balance and need to do force adaptation. And the red is our framework. You can see the robot successfully pull a cart. Yeah. You can see a very clear whole body, upper lower body coordination behavior, right? For this heavy duty task. Yeah, I like this video a lot because it's humanoid help humanoid. This is another example doing door opening. And this is the baseline. You can see similarly, it's a very heavy door. The door is 60 kilo-ish. The baseline, the door barely moves. And this is Unity G1 humanoid. And this is our method. You can see the humanoid works here and use the left arm to pull the door, generate enough clearance, and use the right arm to push the door and make the clearance even bigger, and finally walk through. It's still imperfect, but I think the key is the humanoid can adapt to this forceful task. Okay, so what is the structure here? So the key structure here is a dual agent RO framework. So we found like the humanoid upper lower body has very different dynamics, very different objectives. So we end up designing this framework, which has two policies, two value functions, and two set of rewards. So we have an upper body agent and a lower body agent. But I want to highlight this is different from multi-agent RO settings. It's not decentralized because the policies are jointly trained, and the boost agent have whole body proprioception input. It's just their objective is different. They're still jointly trained. They still have whole body proprioception input. Yeah. And another key structure is actually inspired by optimal control. So we design an adaptive and a feasible 3D force curriculum on an effector because we need to add external force on an effector to teach reinforced learning how to adapt, right? But we need to make sure when we add this external force, FEE, it is feasible. It's not too hard for humanoid, right? So we actually solve in a tiny optimal control problem to figure out what is the reasonable and effective force to satisfy these constraints. Yeah, this is another key structure we figured very important for learning forceful interaction task. Okay, and we can also apply similar architectures to a very interesting hold my beer problem. So in this task, I asked my humanoid to hold beer for me. Surprisingly, it's not easy, right? Because it requires end effector stabilizations because we want the humanoid stabilize in the effector. Here's a demo. I hope you enjoy it. And in this video, my student push the humanoid a lot. And I want a humanoid to stay balanced and don't spilling the liquid. And the right arm, the Coke is our method. The left arm, Fanta or whatever, is baseline. You can see after push, right? The baseline like arm doesn't stabilize very well. The liquid in spilling the liquid, and the right arm can stabilize. I think this video is superhuman. I don't think I can do that. And this is like the humanoid holding a full plate of chips, right? And my student is pushing it, and they still balance pretty well. You can see very clear upper lower body coordination and the composition behavior. Just want to play again. Yeah. Yeah, this is slow. Again, this is slow motion. It's not real time. We slow it down by quite a bit. Yeah, it's actually a heavy push. Yeah, it's a chips. Yeah, and this framework is very similar to agent. And we add another choice, which is slow fast. So we realize upper body is fast dynamic, right? Because we need high precision corrections and fast dynamics. And lower body is slow dynamics, and we need the robust locomotion. So we actually the upper body running in higher frequency than lower body. Upper body we're doing 100 hertz, and lower body we are doing 50 hertz. All right, this is like Sim2Real 3.0, right? We add structures to reinforced learning. We do real to sim. Okay, last slides, I think. Just want to zooming out a little bit, right? I think everything I present so far can be summarized on two axes, right? For all the Sim2Real stuff. So the x-axis is a simulator or model fidelity or like complexity or diversity, right? We start from classic control using reduced order model to full simulator like NVIDIA Isaac, Mojoko, Genesis to like augmented simulator, right? Simulator plus system ID or real to sim. And finally, right, generative simulator, word model, etc., which hasn't happened, but I believe is the future. And the y-axis is when learning happens, right? Because learning can either happen purely offline, like what we did in Sim2Real RO 2.0, or learning can happen online, like MPC, right? Or it can be a hybrid way, right? Or it can be iterative. So in Sim2Real 1.0, right, classic MPC, people use reduced order model for pure online reasoning, right? In Sim2Real 1.5, people upgrade from reduced order model to full simulator, but still only online reasoning. In Sim2Real 2.0, right, we are doing only offline learning using full simulator. And in Sim2Real 3.0, right, we do real to sim. We learn something from the real world, and we do RL++, right, with structures, with better algorithms. So what I propose is we should go to Sim2Real 4.0. I think we need better model, maybe word model, maybe like better simulator. We need better reinforcement learning algorithms, especially learning in the real world. Definitely beyond PPO. We need a off policy, flexible, data efficient reinforcement learning algorithms. And we need better online reasonings. Yeah, that's my take. And the last point I'm trying to make is the combination of online and offline learning could be very powerful. One example is combination of reinforcement learning and optimal control here, right? Just want to give you quick examples. In this example, in this paper, we do both. We do reinforcement learning and online optimal control. Even though optimal control is only using reduced order model, we already saw the advantage. Yeah, the reinforcement learning output a waypoint or like a reference trajectory for a quadratic programming optimal control layer, right? You can see the robot can parkour here, and robot can continuously jump over stairs, which I think is the first time. The quadruped can jump continuously onto this stairs. It's perception based, end to end, and again, this is like hierarchical reinforcement learning and optimal control. Yeah, we can also do like local manipulations, cute demos. The quarterback can push a card. This is pretty cute, I think. Yeah. Anyway, I think I will stop here and ready for questions. Thank you so much. Yeah.
Thank you, Professor Maya. It's really interesting talk. So I have a question about the Sim 2.0, learning from scratch. So without the behavior clone cost or the behavior shaping cost, in the demo, how you can generate the behavior like a human-like behavior? Because it's
we don't have behavioral cloning costs, but remember we still learn from human emotions, right? Because for reinforcement learning, the reward is to track human emotions. So this part actually make the policy look natural and close to human. So the difference from BC is for BC, we directly learn action, the A, right? But here we cannot. Again, like we don't have A from this human emotion. We do reinforcement learning, but the goal is to tracking what human does. So one is direct behavioral cloning, and this is like indirect kind of tracking. Yeah.
What about the learning from scratch?
Oh yeah. For learning from scratch for this one, it's just reward tuning. To be honest, it's just reward tuning and decompose this task into. And I don't think this is very human-like. Maybe it is, but this is like this just reward tuning and yeah.
Thank you.
Yeah, cool. Yeah.
Any other questions?
So, oh, sorry, I forgot to mention, everything I present today is open sourced. So if you're interested, you can take a look at our website. Yeah, thanks. Any other questions? I can take one or two more.
Yeah, maybe I have a question for
go ahead.
So I noticed that current trend in humanoid research try to like focus on purely upper body manipulation and whole body agile control, which we refer to as whole body locomotion. Like, do you think this could be merged in the future, or these two kind of development will still like isolated between each other?
I think that's a very good question. I think they will at some point they will be merged. Yeah, especially again, system one doesn't conflict with system two. So everything I present in the introduction part, like VLA and the whole body part, the second part, they will be synergized at some point. I think that's actually very, very exciting.
Okay.
Yeah,
so
yeah.
How would you imagine the merging of this kind of two change? So obviously speaking, it will be I would say a universal interface between these two kind of system. Like, do you envision that interface will look like through some atomic scale or through some like symbolic links between different kind of tasks you would like to track. So when you have that tracks and tasks, sorry, when you have that task, you will decompose into like several actionable terms to body or the whole body. Yeah.
This is also very good questions. I think that the interface is I think the really mystery to me right now. So people are still doing tracking. I don't think tracking is the best interface. I think it should be some latent.
Actually, no.
Yeah. I think, but we haven't figured out what is the best way. I think that's actually a very exciting research topic. But so far, people are still doing tracking, kind of like you still,
Tracking.
yeah, you still define kinematic pose and doing tracking. Yeah. Thank you. Actually, I gotta go for the next meeting. So, and thank you everyone. If you have questions, feel free to email me.
Okay.
Yeah.
Okay.